Okay, so thank you for the invitation and thank you for the introduction. So this is my first time at Singapore and I really like it. So today I'm going to talk about like a simple local analog of the so-called R-trace formula. In the case when the group is GL2n and the representation R is the ethereal square. And as we'll see in a moment that although this is a simple version, but the geometric side is not that simple in the sense that the geometric side will be some sort of limit of weighted orbital integral. And also finally, so everything I talk today is a joint work with Rafael Bazar Precis, which is there. So, okay, so let me first tell you what is the R-trace formula. Actually, this already showed up in Ali's talk last week. Not this Monday, but last week. So let K be a number field. And let G be a, say, connected, and A's are there. And G be a connected reductive group defined over K. And let R, we fix a finite dimensional representation of the dual group of G. So of the L group to some GL and C. Okay, and now if pi is the cut form of GR del, and we let this Ls pi R be the automorphic L function. Okay, in fact, in Ali's talk last week, he used rho, but here I use R because it's called R-trace formula. Okay, so now let F be a test function on this GR del. And we let this S capital. But I should say, like, the name R-trace formula first showed up in the paper by Jim Arthur, like the problem beyond endoscopy. So he was the first one called this R-trace formula. So if we let S capital 1, F, so be the capital part of the Arthur-Selberg trace formula. Okay, so roughly speaking, this S capital 1F will be summation over all the cut forms that are of Ramanujan type. So of this trace. Yes, stable. Yes, of the stable. Yes. Thank you. Yes. So be the summation of this basic trace pi f, and together with this mu pi, which is a stable multiplicity inside this stable trace formula. Okay. So this if you let this be the capital part of the stable Arthur-Selberg trace formula, and now if we define a new one, which is S capital RF. Which is almost exact same expression as this, except that each representation pi that shows up in the trace formula will be weighted by the order of the poles of this L function. So in other words, we define this S capital RF to be still the summation of pi, so the same pi as here, and we still have this mu pi, trace pi f, but we have an extra MR pi. Well, this MR pi, like in Ali's talk last week, is basically the order of poles of the L function at s equal to 1. Okay, so this is the thing we want to study. And basically, one of the most important goals of this like R-trace formula business is to find a geometric expansion of it. So go is to find a geometric expansion of S capital R F. Okay, so like for example, last week Ali talked about the case when G is GL1 and R is like trivial representation. And I think Mock also have some work on the case of endoscopic case. Okay, so this is basically what the R trace formula looks like. So roughly speaking, you should just think about, okay, it's the original trace formula, but you include the order of poles of the L functions. So now let's talk about a naive local analog. Okay, so now if I let F be a periodic field, and G still defined over F, and so G still defined over F, and R be a finite dimensional representation of the L group still. But this is local, so Ls pi R will be the local L function. For example, you can define the real local long-length correspondence if it's proved for this group G. And don't worry, in a moment we'll move to GLN. Okay, and now let F still be a test function on G. Then we can basically mimic what happened globally to define our local distribution. So I denote it by I discrete R F, which is the summation over all the discrete spectrum. Maybe let me write pi discrete of G, and still of the form like trace pi R, pi F. Maybe there's some stable multiplicity, and then MR pi. Okay, but in this case, since this is local, then the L function you need to shift from 1 to 0. So in other words, this MR pi will be the order of the poles of the local L function at 0, not 1. So it's minus order s equal to 0, Ls pi R. Okay, and then the goal is still to find a geometric expansion of this I discrete RF. Okay, so here I want to make two remarks. I think for example, if it's GLN, then it's just 1. Like it's the thing to make this like stable. Like if your group is not GLN, you have this L packet, and in order to make it stable, you like from global trace formula, you need to have some stable multiplicity in terms of inside the trace formula. But locally, you just mimic. But since we're only talking about GLN, you can ignore it, just 1. Okay, other questions? Okay, so before I talk about the main result, I want to make two remarks. So first, like in general, if G has some non-split center, then we'd better fix the central character in advance, for example, trivial central character, and require all our test functions and the representations has this central character. Okay, and second is, for those of you familiar with this Arthur's local trace formula, this is not of the form of Arthur's local trace formula. Because in the Arthur's local trace formula, as Mock talked on Monday, you have two test functions. You first take the involution of it, then you integrate the kernel diagonally. In other words, your spectral set will have like trace pi f1 and trace pi f2, or more generally, the weighted character. Okay, but since I said that this is a simple analog, so this is the case I know how to do. I don't know how to do two test functions. So this is why I used one of them. Okay? Yes. Okay, so now let's talk about the main result. So from now on, the group G will be GL2N. And the dual group is GL2NC, so let R be the exterior square representation of the dual group. Okay, and like the remark I just said, because G has a non-split center, so we'd better fix the central character. And I don't want to write it for the rest of the talk, so from now on, all the functions and the representations have trivial central character. Okay, so in other words, if I write like summation like pi discrete G, it really means all the discrete series of G or 2n with trivial central character. Okay? Okay, so now, before I talk about the result, I need to tell you which kind of test function we use. And that is the main reason why we call it simple, because we can not do it for all the test functions, only a special kind of test function. So, tell you what is the test functions. So we start with the horizontal Schwarz space. So this curly C, GF, so be the horizontal Schwarz space. Okay, and as usual is with trivial central character. Okay, and then we define that if F inside this space, we say F is strongly cuspital. If the integral of F over all these unipotent radicals, say UF, du is 0 for any parabolic subgroup, say P equal to mu, and a small m inside big MF. Okay, so this is one definition. And this allows us to define two function space. So first is basically this curly C and strongly cuspital, GF. So it's basically the subspace, so F inside this horizontal Schwarz space, and F strongly cuspital. Okay, and then there is the second space, which here I'm following the notation of Wassfield-J. I denote it by C naught of GF, which is all the function F in like CGF, such that not just F itself is strongly cuspital, but all the translation of F is strongly cuspital. So in other words, R, G, F is strongly cuspital. For all G inside the GF. Okay, so here this RG Fx is Fxg. So basically right translation. Okay, so in fact, this space C naught is a very easy space. It's basically spanned by the matrix coefficient of all the discrete series. Okay, so but this space is slightly larger than that. Okay, so now I have our test space, the space of test functions. And besides this, we need one more ingredient in order to define the geometric side of the trace formula. So, and I want to say that the most important feature of this strongly cuspital function is that the weighted orbital integral for this kind of test function is an invariant distribution. So like as we see in like Mock's talk on Monday, in general, the weighted orbital integral is not invariant. But for this special kind of test functions, it is. Okay, so now start with this function F inside this strongly cuspital GF. We can associate a distribution on G, so it's a theta F, the function from G regular F to C, via the weighted orbital integral. Okay, and you will get a function theta F defined on G regular F that is locally constant, which is also locally integrable over GF. So basically, this is very similar to the distribution character theta pi. In other words, if you start with the matrix coefficient of discrete series here, then here you roughly say of pi. Then the theta F is roughly theta pi up to a non-zero constant. Okay, so we have this distribution theta F. And like the character theta pi, this theta F locally also has Chen expansion. So this theta F has Chen expansion. So what this means? This means for any x inside GF semi-simple, we have this theta f locally near this small x of exp capital X is equal to the linear combination of the Fourier transform of nilpotent orbital integral. So in other words, O inside the nilpotent orbit of Gx of this CFO x J hat O x for capital X in Gx regular F close to 0. Here, when I say an element is regular, means it has distinct eigenvalues. Okay, so in other words, this function near every semi-simple element can be written like as a linear combination. So this is a constant. So this is a C. Okay, so a linear combination of this J hat OX. Okay, and this allows us to make the definition we want for our geometric side of our trace formula. So in other words, we define this CFX for any x like this to be basically the average of the germs. So this C is called the germs associated to the regular nilpotent orbit. So in other words, it will be 1 over the cardinality of the regular nilpotent orbit of Gx of the summation of these germs. If this Gx is quasi-split, and it's 0 else. Okay, so, I mean, this definition here is for general G, but since we are only consider G or N, so there is at most one regular nilpotent orbit. So it is either equal to the regular germ if the stable centralized is quasi-split, or in this case split, or just 0. Okay, so this looks a little bit technical, but let me tell you what this really is like in a moment. Okay, so now we have this definition of the notion of germ, we can define our geometric side. So now for F inside Stoney Capital cannot be like this. GF? J hat is the Fourier transform of nilpotent orbital integral. So Fourier transform of nilpotent orbital integral. Okay, other questions? Okay, so now for this test function, we define the geometric side, I geometric F, to be the summation. Recall this G is G of 2n, to be the summation of the torus T over all the elliptic torus of G or N, not G of 2n, G or N, of some normalizer, basically the wire group. This is not important. And the integral over this torus, again, you need to modulate the center, of this CF, the germ I define here, at the point TT, together with some normalizer, basically wire determinant. Okay, so this is really the most important part. The rest are some normalized factor. Okay, so roughly speaking, this geometric side will be about the integral of some germs of this distribution theta f. Okay, so, and now let me tell you, in this special case, what is this CFTT? So, a remark. So one can easily show that basically by the definition that this CFTT is roughly up to some wire determinant, the limit of lambda tend to 1 of theta f at lambda t. So T is an element in this torus, so it's a G or N. Now you diagonally embed into G or 2N. So, sorry, is it T0? Yes. So in other words, it's a singular element because it has a repeat eigenvalue. G or 2N. G is G or 2N. G or 2N, yes. Okay, so basically up to some y determinant, this CFTT is the limit of theta f at lambda tt. So this is the regular element. Okay, but how do we define theta f? Theta f is defined by weighted orbital integral. So in other words, this is the limit of some weighted orbital integral. Okay, so now we have defined our geometric set. So now let me state my main theorem. And you see I plan my talk as well as Yanis, so my main theorem will be here. I don't need to erase it. So theorem. So there will be two parts corresponding to these two spaces. Like this one is the smaller one, so we have a nice result. This one is the larger one, so we need a little bit more. So first, if our f equal to this C naught GF, then this I geometric f defined on the right is equal to literally what we want. Pi inside pi discrete G of trace pi f and MR pi. Okay, so in other words, this is the I discrete RF we want. Okay, and the reason only discrete series shows up is really because this space is very special. Okay, so but how about if we go to that space which are not that special? If f is strongly capital function on GF, then we can show that this I geometric f, then you will not just have discrete series, you will also have tempered contribution. So we are equal to the integral over all the tempered representation of G of this theta f pi and MR pi, E pi. Well, this theta f pi is the weighted character. Okay, and then you can further write it another way, which you can separate the discrete contribution. So it will be the summation of pi discrete. So pi inside pi discrete of G. Because in the discrete series case, the weighted character just becomes the trace. So trace pi f MR pi plus the remaining terms. So the integral over pi discrete G minus pi tempered, the opposite. Of the pi tempered G minus pi discrete G of theta f pi and R pi D pi. Okay, and this part is really this IR discrete f. Okay, so in other words, for this kind of test function f, we can have a geometric expansion of this so-called local R trace formula, where the geometric side is given by, roughly speaking, some limit of weighted orbital integrals. Okay, any questions? Okay, so now before I talk about the proof, let me make two remarks. So remark. So the first remark is the second part of the theorem follows easily from the first part. So which is 1 implied 2 is easy. So we'll only talk about the proof of 1. So we only consider 1. Okay, and then the second remark is we can also actually very easily also can prove an analog formula of 1 when the case when I is a symmetric square. So we can prove an analog formula is 1 when G is G to N and I is symmetric square. So you just need to use the fact that if a discrete series is self-dual, it's either symplectic type or orthogonal type. So this is not a big deal. Okay, so now we basically need to focus on how to prove 1. So now let me talk about the proof of 1. Okay, so the main idea of our proof is that we want to understand what is this pole means. And the main technique in our proof is we relate the poles of this local L function to certain multiplicities of spherical varieties, which is the one so-called Shalaga model. And then we basically prove a local trace formula for the Shalaga model. Okay, so now in order to prove 1, let's define a subgroup. So we define a subgroup H inside G. Let me remind you this is G to N. To be H will be this diagonally HH and then INX, where H in G of N and X is N by N matrix. Okay, so this is called the Shalaga subgroup. And then we define a character on this group. Get a feeling I better not erase this. So then we define a character chi from HF to C cross by mapping element of like HH, INX, map it to psi of trace X, where psi is a fixed additive character. Some character F to C cross. Okay, and then for pi, be an irreducible representation of G of trivial central character as usual. Then we can define the multiplicity M pi to be the dimension of the home space, home HF pi chi. Okay, and then there is a theorem. A lot of people, let me first state the theorem, is that if pi is a discrete series of G, then M pi is non-zero if and only if the local exterior square L function has a pole at 0. So Ls pi R has a pole at s equal to 0. And moreover, since one can know that this part, the Shalaga model is a Gelfand pair, also this pole is at most a simple pole. In other words, both sides is less or equal to 1. So moreover, we'll have M pi just equal to the order of poles. At s equal to 0. So in other words, equal to our MR pi. Okay? So in other words, we find a relation between this MR pi, which is the thing we want to understand in the trace formula, with the multiplicity of certain spherical varieties. And so when we start working on this Shalaga model, we saw that it has already been proved for all the discrete series, but it turns out it's not. So first, this was first proved by Zhang, Nian, and Qin for the supercuspidal case. So when pi is supercuspidal. And then Kiwat proved one direction of it for all the discrete series. So in other words, he proved that if L has a pole, then multiplicity is non-zero by using some Rankin-Selberg integral. And then basically in our paper, we just finished the other direction for all the discrete series. But our proof really just used the method by Zhang, Nian, and Qin. Their method is quite general for this direction. Okay, any questions? Okay, so now if we have this theorem, what it tells us it tells us that in order to prove our trace formula, we just need to prove another thing. So as a result, in order to prove, let me give this a name, say star. So in order to prove star, it is enough to show that this I geometric F, unfortunately I just erased it, so there will be some integral of germs, is equal to what I will call I spect of F, where this I spec F is the summation over all the discrete series of trace pi F M pi. In other words, the multiplicity of Shalaga model, because we know M pi equal to M R pi. Okay, and let's call this double star. And this double star is what we call it a local trace formula for the Shalaga model. Oh, G, yes, thank you. Sorry. G, yes, it's all the discrete series of GL2M with trivial central character. Okay, other questions? Okay, so now before I talk about how to prove that, let me talk about another consequence of this trace formula. Let me go here. So one application. Of this double star. Okay, so I need one preparation. So for pi inside this discrete series, let me define a similar expression as I geometric F. I'll call it M geometric pi, which is basically the exact same formula. So T inside all the elliptic torus of GLN, and you have this wire group, T inverse, the integral over TF called the center. But in I geometric F, we put CFTT, which is the germ of theta F. Now we put C pi TT. Okay, so this guy will be the germ of theta pi. In other words, the distribution character of pi. And then the same normalized factor, y determinant, t squared dt. So in other words, this will be something depends on theta pi. Okay, so then a corollary of this double star will be, it has two parts. So pi is a discrete series of G. So first, we will have this M pi which is the multiplicity of the Shalaga model equal to M geometric pi, which is something depends on the distribution character theta pi, and equal to MR pi, which is the order of powers of L functions. So in other words, the first equation gives you a multiplicity formula for the Shalaga model. While the second equation gives you a relation between the local L function and the distribution character theta pi. Okay, so this is the relation between theta pi and L0 pi R. R is wedge square. Okay, so this is the first corollary. And the second corollary is, the second part is that the following are equivalent. Probably don't have enough space here. So it says the following are equivalent. First is this M geometric pi equal to 1 or non-zero. It must be either 0 or 1, by the way. And the second part B is this Ls pi. R has a power at S equal to 0. The last part is pi belongs to the image of the functoriality from SO2n plus 1 to GO2n. Okay, what this means? This means we give a condition on the distribution character theta pi, not the twisted character. Like we give a condition on this theta pi of whether pi belongs to this image of this endoscopic functoriality from classical group to GLN. Okay, so this is basically the corollary of this trace formula for Shalaga model. Defined by endoscopy, right? Yeah, by endoscopy. Yeah, I cannot define functoriality by this. Like, is it defined? Other questions? Oh yes, pi is discrete series. So, is it the Lagrange ideal function? Oh, the exterior square. I is the exterior square. Sorry. Yeah. Okay. Other questions? Okay. So now let's. Okay. So now we talk about the corollary. So now let's prove this trace formula. So let me still remind you what is this geometric side. So this I geometric F will be the summation over T elliptic of the wire GLN T inverse the integral of TF called the center of CFTT and the Y determinant square dt. Okay, and we want to show I geometric F equal to I spectral. Okay, so now let's talk about proof. Now I can erase this. So in order to show that this I geometric F equal to I spect F, we need to define something in between. So in other words, we want to define a distribution IF, and then we show it equal to I geometric and I spect separately. So for F, inside this test function C0 GF. So now we define, actually we don't need, we can do more general, like Johnny Caspito. So we define this distribution IF to be that because we want to do something about Shalaga model, so it only makes sense if you integrate over H first. So integrate over HF. As usual, there's a trivial central character, so you modulo the center of F of H and against this character on the Shalaga subgroup. And perhaps there's the inverse, but doesn't matter. DH. And afterwards, you have to integrate over GF called HF diagonally. So in other words, this acts by conjugation, DG. Okay, so this will be the distribution in the trace formula. And a fact is that this two integral is absolutely convergent in this order, but as a double integral is not absolutely convergent. So this is why when we prove the geometric side, we need to add some truncation factor here. Okay, and then in order to prove this double star, we just prove the following. Which is First, for all strongly cuspidal functions of G, we have IF equal to I geometric F. And the second part is that for all F inside C naught GF, we have IF equal to I spect F. So if you combine this, you know I spec equal to I geometric for F inside C naught. Okay, so how are we going to prove it? Well, first, let me say that the spectral side is easy in the sense that we not only can do it for Schrödinger model, it actually works for much general spherical variety. So it's easy. So we'll focus on the geometric side, which is where the question is. So we'll focus on the geometric side, IF equal to I geometric F. Okay, so now let's see. So now if we write this definition of IF explicitly in terms of matrix, what will it be? So we use the Iwasawa decomposition. And here I'm ignoring the compact integration. So ignore. In fact, you can integrate K on both sides first, so it's not important. We know that this IF is equal to the integral over GLN, then another integral over GLN by modulo the center, and the integral on n by n matrix denoted by the Lie algebra of GLN of f of G inverse 1 HH IN X G1. And with the character per psi trace of X, dx, dH, dg with some determinant G to the n. Okay, so basically roughly the inner two integral are integration over H, because this is how we define H. The outside GLN is roughly G co H. Because you use Iwasawa decomposition, you only need to consider this NM parabolic. Then its quotient with this H is just one GLN. Okay, because H is diagonally GLN. Okay, but then, like I said, this double integral is only convergent in this order. It's not absolute convergent as a double integral. So we need to introduce some truncated function to make it work. So we introduce a series of truncated functions. So this is actually not that is important. You just need to put a very weak condition on this kappa n. So this is infinity of GLN F for n great, so basically a series of it. And then you define this INF to be the same expression, but I put the truncation here. Okay, and in particular, I have this IF equal to limit n tend to infinity of INF. Okay, so then and the good part about this is now I can change the order of integration. Okay, so now I just need to study this INF. And then, yeah, I don't want to erase it. Then you realize something. Like our geometric side here is basically support on this TT. So in other words, we support on the elliptic regular element of this H. So this gives us a hint that we should use the Y integration formula. So by using the Y integration formula, on H, on this HH, we get the following. We get this INF is the summation over all the torus, not just the elliptic one, all the maximum torus of, I will ignore the Y factor, TF, call the center, y determinant times basically some kind of weighted orbital integral. Of this f of G inverse H inverse TT IN X GH times something depends on this kappa, this truncation. Okay, so this is what you get after you apply the y integration formula. So this looks complicated, but it's actually not that bad. So we'll be integral over all the maximum torus of, roughly speaking, some weighted orbital integrals on this singular element, TT. Okay, and then it comes the most technical part of the proof, which is that in this integral, the weight are given by this kappa nt, which is something basically depends on this kappa n. We fix this truncated function, kappa n, and of course the torus t. But this is not a very nice weight. Okay, so then we need to change the truncated function to some nice weighted factors, and also take n go to infinity. Once you do this, you can show that this IF, which is limit n tend to infinity INF, is equal to summation of all the maximum torus of t and the integral over this t of some singular twisted weighted orbital integral. So singular twisted weighted orbital integral at tt dt. And what is this twist? This twist is what we denote by theta, which will be the adjoint of this matrix IN, anti-diagonal one. Say it again. Oh, yes, thank you. Sorry. So dt. Okay, and then we show that, you see, this it's very hard to study this singular twisted weighted orbital integral. So then we show that this will equal to the same t, and the TF called the center of limit lambda tend to 1 of the regular twisted weighted orbital integral of this regular twisted, still the same twist, weighted orbital integral at lambda t dt. Okay, and then it comes the last step. So now if you compare here and here, there is an apparent difference. Here is all the torus, so all the maximum torus in GLM. But here you only have the elliptic ones. So now then we have two steps. If T is not elliptic, by using the fact F is strongly cuspidal, we can show that this this twisted orbital integral, weighted orbital integral at lambda t is 0. So this part is done. Now if T is elliptic, and you find, by the way, we define our twist. Actually, the twist for elliptic torus becomes trivial. And it turns out, as a result, this twisted weighted orbital integral at this lambda t is just equal to the usual weighted orbital integral defined by Arthur. So like just equal to weighted orbital integral. At lambda tt. And once we take the limit, lambda tends to 1 of these things, and you should remember, as we write perhaps half an hour ago, this just gives us the germ. So this gives us CFTT. And this basically proves the trace formula. So this gives us IF equal to I geometric F. Okay? Okay, that's all. Thank you very much. Yes. Yes. Yes, G equal, roughly speaking, yes. Yes. No. Yeah. Actually, this expression of IF was first introduced by Wasfilje in his proof of the local orthogonal Gangros-Prasad. And for all the cases afterward, we need to use this IF. So you can define it for all the GH. You integrate H first, then integrate over diagonal G equal H. Yes, you change this to the standard twisted weight we defined at this point. Oh yeah. Oh yeah, this is the most technical part. It takes us 20 pages. So you have to cut the domain nicely such that in the middle part they are equal, and on the outside part both are 0. So this is the most technical. Oh, it doesn't change. The IN doesn't change. Yeah, as long as it's both in the nice position. Yes. And then you take n to go to infinity. Yes. Yes, but that is easy because, what does this tell us? Basically, this trace formula essentially tells us. Do you remember we have this m geometric pi, which is something depends on theta pi, and equal to this mr pi, which is the order of poles of the exterior square. So I is the exterior square. Okay, but then you can do a very easy thing by define a new m geometric. Say, I define this m geometric pi prime to be what? To be the summation over all the elliptic torus of GL2n, not GLn, GL2n of, I think is the TF modulo the center of this theta pi t square, perhaps some y determinant like dgt dt. So basically, this expression tells us when will pi be self-dual. But if pi is self-dual, it's either symplectic or orthogonal. So if you use this minus m geometric pi, then you get this symmetric square. Yes. Say it again, sorry. We only use the fact that if you start with this, say, GL2n, discrete series, and you induce it to SO4n. And if the induction is reducible, then the L function will have a pole. Yeah, we use that, yes. Yeah, otherwise we cannot prove this multiplicity related to the poles. Yes. Thank you.